Dendritic integration is the fundamental process by which a single neuron computes the thousands of synaptic inputs it receives before deciding whether to fire its own electrical signal, an action potential. Rather than just acting as passive wires that funnel electricity to the cell body, dendrites are highly complex microprocessors. They calculate incoming excitatory and inhibitory signals in real time, allowing a single neuron to perform sophisticated mathematical operations. The two core dimensions of integration. When neurotransmitters cross a synapse and bind to a dendrite, they create tiny electrical fluctuations. For the neuron to fire, these tiny fluctuations must sum together to cross specific voltage threshold at the base of the axon hillock. This summation happens in two primary ways. Spatial summation. This is integration across space. If multiple synapses located on different dendritic branches receive signals at the exact same time, those localized voltage changes travel towards the cell body and add up. Temporal summation. This is integration across time. If a single synapse fires repeatedly in very quick succession, the new electrical signal piggybacks on the lingering voltage from the previous one, building up to a larger total charge. Passive cables versus active microprocessors. The theoretical understanding of dendritic integration has evolved significantly over the last few decades. The classical view, or passive cable theory. Originally developed by Wilfred Rahl in the 1950s and 60s, cable theory modeled dendrites as passive, leaky electrical cylinders. In this model, as an electrical signal travels down a dendrite towards the cell body, it gradually loses strength, like water leaking out of a holy pipe. If a synapse was located at the very distal tip of a dendrite, its influence on the neuron's final output was considered extremely weak compared to synapse close to the cell body. This model assumed integration was mostly linear, simple addition and subtraction. The modern view, or active dendrites. We now know that dendrites are not passive cables, they are electrically active. They contain their own voltage-gated ion channels, sodium, calcium, and potassium. This fundamentally changes how integration works. Dendritic spikes. If a local branch of dendrite receives a strong enough cluster of inputs, the voltage-gated channels in the dendrite itself can open, generating a localized mini-action potential, or a dendritic spike. Nonlinear integration. Because of these active channels, a cluster of signals arriving together doesn't just add up mathematically, i.e. 1 plus 1 equals 2. They can amplify each other exponentially, i.e. 1 plus 1 equals 5. Conversely, inhibitory inputs placed at strategic choke points on the dendrite can completely veto massive amounts of excitatory input. Why this matters. Dendritic integration theory explains why the brain is so computationally powerful. If dendrites were just simple passive funnels, a single neuron could only perform basic addition. Because dendrites have active properties and complex branching geometries, different segments of the dendritic tree can perform independent computations like multiplying, dividing, or acting as logic gates such as an and/or operator. This means the computational power of the brain isn't just determined by the network of connected neurons, but by the massive localized processing power contained within the limbs of every single